welcome to the solutions of revision worksheet 18. So this revision worksheet had two questions. The first one was from the DEB 2017 mock. It was paper 1 section A question 4. So it was a differentiation question. And the second question was from DEB Mock 2017 again, paper 1, but this time it was a section B question 9, which was a 50 marker. So it was in the problem solving section, but it was a calculus based question. So pretty much dealing with integration. So let's get started. So this is question 1 part A. A curve is defined by the equation x minus 3 squared plus y squared is equal to 25. So you have a few different options here. The first option is to work with this exactly as it is. So to not multiply out that bracket, to leave it as it is, and to use what we call implicit differentiation. So that is where we don't have a function in the form y is equal to something, something, something. Instead, we end up with a y that's not easy to isolate, for example, a y squared, like in this circle. We can isolate the y using square roots, but it just complicates our differentiation. We will get the same answer if we did it that way. In this part, for the actual formula of the slope, it would look a little bit different. However, if we actually were to sub in values, it should give us the same thing. Now, the second option, so the first option is to leave the bracket as is. The second option is to multiply out that bracket but still use implicit differentiation. And then the third option is to isolate the y. It depends on you, and it depends on how much you like using the chain rule. I don't mind using the chain rule, so that's the method that I'm going to go. So we're going to start here with x minus 3 squared plus y squared is equal to 25. So implicit differentiation means we're going to differentiate everything here with respect to x. Now, if I multiply everything here with respect to x, what I get is 2 times the bracket. So I brought down my power in front and I take 1 away from the power, 1. And then I multiply it by the derivative of what's in the bracket, which is 1. I then differentiate my y, which gives me 2y. However, because I'm not differentiating this with respect to x, I have to then put in a dy dx. I then have equals, and my 25 will differentiate to 0. So now all I need to do is do a little bit of cleanup. So I end up with 2 bracket x minus 3 plus 2y dy dx equals 0. If I do a little bit of manipulation here, I get 2y dy dx equals minus 2 bracket x minus 3. And to get dy dx on its own, I'm then dividing both sides by 2y. X minus 3 all over 2y. Now, a little bit of cleanup happens here. My 2's cancel. And I'm going to multiply in that minus on the top line. So that gives me minus x plus 3 over y, or I would prefer to write it as 3 minus x all over y. So that is using implicit differentiation. If you'd multiplied out the bracket first, you could have still used implicit differentiation, but you wouldn't have had to use the chain rule. That would have been the only difference, and some people might have found that a little bit easier, and that's perfect. But like I said, if you tried to isolate your y, and to work with it then, you would have ended up with a square root, which is working definitely with the chain rule. And your answer would look different to what I have here. However, your slope would actually work out to be pretty much the same. What would happen if you isolate your y is instead of the y on the bottom line here, you would have a function in terms of x for y, if that makes sense. So it would be 25 minus the x minus 3 squared all under a square root. So it would look pretty complicated. Now, just to bear in mind, every time you do a question which looks at differentiation, remind yourself that when you do dy dx that you're actually getting the slope. Because see here, the next part of the question says, hence find the equation to the tangent to the curve at the point 6, 4. So they've given us a point which gives us an x and a y. And the formula for getting the equation is y minus y1 is equal to m bracket x minus x1. Now, I can, of course, use my point, however, I'm missing my m. M is equal to slope. And we've just worked out a formula for slope. And ours is 3 minus x all over y. And if I stick this in, instead of x, I'm putting in my 6 for my point. Instead of my y, I'm putting in 4, which gives me minus 3 over 4, which is my slope at that point. So I get y minus, I sub in my 4 for y1, I get minus 3 over 4, bracket, x minus 6. Now, I'm going to bring the bottom 4 across the equals, or think of it as multiplying everything across by 4, and I get minus 3, x minus 6, and now we're just going to do some cleanup. 4y minus 16 is equal to minus 3x plus 18. So what we get here is 3x plus 4y, and that should give us a minus 34 equals 0. Now, they didn't specify what way they wanted that, so if you left it as y is equal to mx plus c or something like that, that's absolutely fine. So as long as all your bits are here, the signs may have changed depending on which side of the equals they are, but this should be the equation of the tangent at the point 6, 4. So the next one is show that the curve 2 over x minus 3 has no turning points and no points of inflection. So there's two parts to this question. So let's work with the first part. So the first part, so actually I shouldn't really call it I because it is I. So I'm going to, okay, so the first part here is asking me about turning points. So if you remember, how do we get our turning points? To get our turning points, we get dy, dx, and we let it equal 0. So let's start with our y, and that's 2 over x minus 3. Now we can't work with that. Well, sorry, you can of course work with that using our quotient rule. However, because the top line is actually just a constant, I would be more inclined to bring this bracket across or up over the line and use our chain rule here then to differentiate. Just a little bit quicker, but using the quotient rule you should get exactly the same thing. So we bring down 1 from the power. Okay, then we take 1 away from the power, which gives us minus 2, and then we multiply by the derivative of what's in the bracket, which is 1. Now, cleaning that all up gives us minus 2 all over x minus 3 to be squared. Bring it back down under the line. So if I want to get the turning points, I'm going to let that equal 0. So I put minus 2 all over x minus 3 squared equals 0. If that was the case, then multiplying both sides by x minus 3 squared, I would get minus 2 equals 0, which it does not. So what we would have here, therefore y has no turning points. Okay, because it doesn't exist. The second thing we're asked to do is points of inflection. So for points of inflection, we would let d squared y dx squared equal 0. So we want to take our dy dx, which was minus 2 all over x minus 3 squared. I'm going to write this again using the chain rule just to make life that little bit easier. I know people might want to multiply it out and use the quotient rule, and that's absolutely fine. I'm going to then get the second derivative. So going to differentiate this again, and I'm going to bring down my power. My minus 2 is already there. I'm going to take 1 away from my power, which gives me minus 3, and I'm going to multiply by what's there. By the derivative of what's in the bracket. So that works out for us as 4 all over x minus 3 cubed. Now, I'm going to let that equal 0, so we have 4 over x minus 3 cubed equals 0, but just like before, multiplying both sides by the denominator gives me 4 equals 0, which is not true. So therefore, y has no points of inflection. Okay, so just some bits and pieces about this part. The first one is do kind of look at the chain rule that I've used here and see, you know, is it something that you could work with, because it does simplify your sum, and it does go a lot quicker than trying to use the quotient rule. I would generally say, as a general rule, use your quotient rule if you have variables above and below the line. If you have, like in this case, a constant on the top or constant on the bottom, I wouldn't necessarily be using the quotient rule. The second thing to be careful of is a lot of people, when they do this question, see, I'll just mark it at this point here. So at this point here, they would then say minus 2 is equal to that bracket squared, because they kind of bring it above the line, and they forget that it's actually 0 multiplied by that bracket, which would still be 0. So just be really careful with your multiplication there. The third thing that I'd say about this is do make sure you're finishing your questions. So it's not enough to kind of me going minus 2 does not equal 0. I need to kind of demonstrate that I know what I'm talking about. I know what I've got to. So having just that quick line of therefore y is no turning points takes a second to write, but actually it's really showing that you know what's going on in this question. Same with the points of inflection. Not a huge amount of space there. Especially if you were trying to use the quotient rule. So just be careful and try to keep things as neat and tidy as possible. I know I'm not really doing a good example of that, but do bear in mind that I'm trying to write on my screen. So the last part here, part 2, is comment on the shape of the curve for all x element of or, the real numbers. So I'm just going to sketch out for you what this graph actually looks like. And it's always a good idea to do the sketch. So what this is I have a curve that is basically coming down like this, and one that goes here. Now, there's two parts. There's a break in the graph at x equals 3. And the reason that I know there's a break in the graph at x equals 3 is because, sorry, now I've actually messed this part up, is because if you take a look at our original, still not great, if you take a look at our original y here, okay, our original y is y equals 2 over x minus 3. Now, for that function, when I sub in x equals 3, I will get a 0 on the denominator, and if I try to divide any number by 0, I will get an error. You can try it in your calculator. 2 divided by 0 is going to give me an error. It cannot work. Therefore, there is no value for y that exists when x equals 3. This is what we call a discontinuous graph. And we have this idea that when x is equal to 3, that no value exists. So each of these parts of the curve are getting closer to x equals 3, but there is no actual value for x equals 3. There's actually a break. What that line is called is an asymptote. Okay. So we have what's called two asymptotes, and the two asymptotes at x equals 3, which I've just shown you, and there's another one at y equals 0. So for y equals 0, it's not defined. And again, look at our equation and see if I put in 0 for y, I'll get 2 equals 0, which does not exist. So again, my y equals 0, i.e. my x-axis is my second asymptote there. So if we take a look at the function itself, and we can work with dy dx, and using from above, my dy dx is 2 all over x minus 3 squared. I should have a minus here. Yeah, perfect. Now, take a look at this for a second. On the top line, I have a negative number. On the bottom line, I have a positive number. So top line, straightforward. Bottom line, how do we know for sure that that is a positive number? Well, we would have learned that any real number squared is going to end up being positive. So it doesn't matter what x minus 3 is, no matter what number that is, once we square it, we're actually getting a positive number. So if I have a negative number divided by a positive number, it's definitely going to be negative, i.e. it's definitely going to be less than 0. What that means, so sorry, I'll just put this in a box because that's kind of like one piece. What this means for us is that the curve is decreasing for all values. Okay, so decreasing for all values of x. And take a look at the graph. So at question 2, this is from the 2017 DEB Mock as well, question 9. So it's coming from the section B part. It's more problem solving. This was worth 50 marks. And it was a calculus question, but it was actually a calculus question that was pretty much based on integration. So let's take a look. It says the acceleration of a particle in meters per second squared moving in a straight line at a particular time interval is given by the acceleration is equal to 1 over t squared plus 3t, where t is between 1 and 5 inclusive. It tells us t is the time in seconds from the instant the particle begins to move. They tell us that the speed of the particle is a half after 1 second. Find its speed at 5 seconds. Now, what's really important to note for these particular types of questions is how our distance, or displacement if you like, velocity, and our acceleration are linked. And they're linked in a very specific way, because my distance can be differentiated and get velocity, and velocity can be differentiated to get acceleration. So this is my differentiation. By that same logic, the acceleration can then be integrated. So the opposite of differentiation, integrated to go back to velocity, and velocity can be integrated to get back to distance. So that's really, really important. Now, we're starting at acceleration, and because we're starting at acceleration, we want to be able to get to our velocity, so we're going to have to use integration. So let us integrate. We're going to integrate 1 over t squared plus 3t. When we integrate, we also have to have this dt. So remember, your integral here must then be given, or must be followed by a dt or a dx. This is effectively multiplied by the dt. And when you integrate, then that integral and the dt will disappear. Now, we have no limits of integration here, so what we have is an indefinite integral. So before we integrate, it might be easier to write everything as a power. So we have t to the power of minus 2 plus 3t, and this is all dt. Now, when I actually integrate, I'm going to use my rule, which says add 1 to my power, which gives me minus 1, and then divide by my power. Add 1 to my power, and divide by my new power. Now, because we're not using limits of integration and we're using the indefinite integral, we have a plus c. So this is my velocity. I'm going to call it v. Now, obviously it's not going to be terribly useful for me if I have a c, the constant that I don't know. However, remember in the question they said the speed was equal to a half, or velocity was equal to half, when time was 1 second. So we're going to sub that in. We're going to say, well, when v is a half, I can sub in 1, and I can sub in 1 here, and I should be able to work out my c. So I get a half equals minus 1 plus 3 over 2 plus c, and when I work that out, we end up with c is equal to 0. Okay, so now my formula for speed, but rather we would call it velocity, is t to the power minus 1 over minus 1 plus 3t squared over 2 plus 0, doing a little bit of cleanup, that's minus 1 over t plus 3t squared all over 2. Now they want us to find the speed or velocity when t is equal to 5. So what we're going to do now is sub that in. So v is equal to minus 1 over 5 plus 3 times 5 squared over 2. And that gives me 37.3 meters per second. Or you can write ms minus 1. Both are fully correct. So just be careful. Often students get a bit confused here about the limits of integration. If we just want to go from acceleration to velocity, there is no limits of integration. We're just getting a general formula. However, they do give us a little piece or a little taste here to show us that actually when we get here, we can work out our c. Okay, so the next question then says find the average speed. Now, be so careful here. If you see the word average on the course, 99% of the time it will relate to the average formula of integration. And that formula is b minus a integrating between a and b of any kind of function. Okay, now we want to get the average speed. So what we need to do is what's in here, we're going to replace that with what we know as speed. Not the original, so definitely not what we had for acceleration. We want to get average speed. So b and a are given us here as the intervals, so we go between 1 and 5. Remember, a is always the smaller, b is always the bigger. Our formula, if you remember, for velocity is minus 1 over t plus 3t squared all over 2. And we're integrating with respect to t, so we have a dt here. So we get a quarter, and we're going to integrate. Minus 1 over t is minus the natural log of t, plus 3t cubed all over 6. And we want to integrate that between 1 and 5. Remember, you're adding 1 to your power, then dividing by your new power. We already were dividing by 2, so if we divide by 3, it ends up being like a divide by 6. So we have a quarter. When I sub in a 5, we end up with minus the natural log of 5 plus 3 times 5 cubed all over 6 minus the natural log of 1 plus 3 times 1 squared all over 6. And that can pretty much all go into your calculator. And what you'll get is 15.09764. But keep in mind that they want this to 2 decimal places. Always keep in mind what way they want your answer. So this actually goes 10 meter per second. speed is measured in meters per second. Sorry now. Try again. 10 meters per second. So part B of this question kind of goes away from what we're working with from part A, which was integration, and it's using now a different type of integration. So the proposed level of new roadways is achieved primarily through a series of cuts and fills, taking earth materials from one area and using it somewhere else. The diagram shows a vertical cross-section of a roadway through a particular terrain. The proposed elevation of the roadway is 14 meters above sea level. Therefore, a cut is required at the points A and B. Using the coordinate plane with the y-axis as the initial point of the cut and the x-axis as sea level, the elevation of the terrain can be described by the function 32 minus 2 times x minus 3 squared, where both x and f of x are measured in meters. Find the coordinates of A. So, what we do know about A and B is both of them have a y value of 14. From the graph, it's very easy to see, well, A is actually going to be 0, 14. But what's B going to be? So we want to find, well, where is our function equal to 14? So to do that, we get 14 is equal to 32 minus 2 x minus 3 squared. Now, again, you've kind of two options to work with this. I prefer working with, this is complete the square that you would have seen in functions last year. What I would prefer to work with it in this form, I would not multiply out the bracket. I think multiplying out the bracket is going to cause more work. You're going to end up with a quadratic, and you're probably going to use minus b to solve it, or you may use guide number, but anyway, it is longer. So just to remind you that we do have a method when it's in this format that we can use. So I'm going to use that method. So first of all, I'm going to bring the 32 across, minus 2 times x minus 3 squared. So what we get here is minus 18 is equal to minus 2 x minus 3 squared. I'm going to divide both sides, so I get 9 is equal to x minus 3 squared. So just to make life a little bit easier, I'm just going to switch sides. So I get, well, x minus 3 squared is equal to 9. I'm going to take the square root of both sides, and when I do, that will give me plus or minus the square root of 9. So I have to remember, if I decide to take the square root of a number, I can get either the positive or the negative. So now I get x minus 3 is equal to plus or minus 3. So x is equal to 3 plus or minus 3. So working out the two values, I get x, so this is the positive one, x equals 6, and down here, using the negative one, I get x equals 0. So I already used my 0, so my b must be 614. Now, if you used the idea of multiplying out that bracket, cleaning it up, using minus b or guide number, hopefully you can see how much simpler this is, how the maths is much nicer, how much shorter it is. So when we have something in square form, we always have the ability to use this idea. And it is definitely one to remember, so that you are, working smart, because that's what you want. You don't want to be doing work for the sake of work. You want to work as efficiently as you can. So it then says use the trapezoidal rule and the interval widths of 1 meter. Now when it says interval widths, what it means is h is equal to 1 meter. And to find the approximate area of the shaded cross-section of earth material to be excavated between the elevation of the terrain and the proposed elevation of the roadway. So first thing we're going to do, we're going to go to page 12 of our log tables. And on page 12, we have the trapezoidal rule. And the trapezoidal rule tells us that A is approximately, so remember this is approximation, it's approximately h over 2, where h is the width. And look at the diagram on page 12 to remind you of that. And we have y1 plus yn plus 2 times y2 plus y3 plus y4 all the way up to yn minus 1, so the second last one, and that's our formula. So we're going to work between x equals 0 and x equals 6. So they were our 2 points that we found at either end. So again, you have 2 options to work with this. I'm going to work out my height at each of these points, f1, f2, f3, f4, f5, and f6. So just to remind ourselves, just because I don't have it in front of me, but the function is given as 32 minus 2 times x minus 3 squared. So when you work through this, you get this as 14, you get this as 24, you get this as 30, here as 32, here as 30, here as 24, and here as 14. Now, again, I keep saying this, but it's true. You have 2 options. Now, bear with me while I try and sketch this out, because I don't have the diagram here in front of me. So we have, roughly speaking, this shape here. And the shaded piece is here. Okay, and we've just worked out our series of heights here and here. And we've worked out kind of the next one. We've worked out the next one. And we've worked out this one. And this one and this one. So like we've worked out all these heights here. Now, as you can see, what we'll end up working, and I'll use my highlighter to show you, we're going to end up working out all of this piece here. And that's not what we want. Sorry, I'm after going too far. So what we're going to work out is over to here. We're not going to go beyond this line. So we're going to work out this piece here. Now, that's obviously more than what we need. So we have 2 options. We can consider where this line is, and remember that this line here that I draw across is y is equal to 14. So one way that I could work this is that I could reduce all my heights by 14. So take away 14 from each height. So I get 0, I get 10 minus 14, I get 16 minus 14, I get 18 minus 14, I get 16 minus 14, I get 10 minus 14, I get 0, and they become my new heights. That's a very straightforward way to do it, and that would be a way that I would definitely recommend you to work. What that means is you go straight into your trapezoidal rule, and that's your answer. If you don't, okay, so that's kind of like option 1. If you don't, and you use the original 14, 24, 30, 32, 30, 24, 14, what you need to remember is you've included this rectangle here. And this rectangle here, that area is going to be included in what you've got from the trapezoidal rule. So remember, this starts at 0 and goes to 6, and the height is 14. So effectively, this area is equal to 6 by 14. And when you work out 6 by 14, we get 84. Okay, and that's meters squared. So whatever you get from your trapezoidal rule, you'll have to take that away. So in this case, you'll get 154 meters squared from the trapezoidal rule. You'll take away your 84 meters squared, and you'll get your 70 meters squared. So if you got this answer, you just forgot to take away the piece that wasn't shaded. Now, I'm going to proceed with this using the first option, so the adjusted heights. So my adjusted heights here are 1 over 2. My y1 is 0, plus my yn is 0, plus 2 times 10 plus 16 plus 18 plus 16 plus 10. And when you work all that out, you should get 70 meters squared. And that's your final answer. So just bear in mind that there's two ways. Now on the worked solution, I've actually worked through the second method there. So I just wanted you to see both methods. The only difference is you have a little bit of what would we call, you need to basically take account for that bit that's not shaded. You do that at the end of the second method, whereas you do that for the start of the first method. Both are absolutely fine to do, and it's really which one you prefer. But don't forget that sometimes when we use the trapezoidal rule, we may not be getting the full area of what we want. Sometimes we might be getting more than what we want, and we have to take something away. So then it asks us to use integration. Now, when we use integration, it's really important to remember that integrating between 2 points, which is what we're going to do, we're going to have to take away that bit that's not shaded. So first of all, I'm going to start with my function. So my function here is 32 minus 2 times x minus 3 squared. Now, I'm not going to integrate like this because it's not possible to do so. We don't have enough knowledge to integrate brackets. It can, of course, be done, but it's not something we need to know how to do. So we're going to instead multiply out the bracket. And when we multiply out the bracket, we're going to clean this up. And we end up with minus 2x squared. Plus 12x minus 18, which gives us minus 2x squared plus 12x plus 14. Now, notice that this is my function. It does not equal 0, therefore it cannot change its signs. It is a function. If it was equal to 0 or equal to some number, then I could change my signs. But at this point, I have to work as is. So now, I want to integrate between 0 and 6, my f of x, with respect to x, which gives me between 0 and 6, I'm going to integrate my minus 2x squared plus 12x plus 14 dx, which is going to give me minus 2x cubed divided by 3. Plus 12x squared divided by 2 plus 14x, and this is between 0 and 6. So when I work that out, it should work out at 156 meters squared. However, this includes area not shaded, and that's important. And the area not shaded, as I showed on the last slide, which was 14 by 6, which is 84 meters squared. So area shaded is equal to 156 minus 84, which gives me 72 meters squared. So as you can see, the actual area is a little bit higher than what we got using the estimation of the trapezoidal rule. But they're in or around, so we had 70 using the trapezoidal rule and 72 using our integration methods. Now, the last part of this question says an alternative proposal is to construct the new roadway at an elevation of 24 metres above sea level. Find, correct 2 decimal places, the percentage reduction in the cross-section material to be excavated if this proposal was adopted. So basically it's saying, well, look, we're going to get a smaller shaded area, and what's the reduction? So this seems like a straightforward question. However, we have a little bit that we do need to do. So the first thing we're going to do is we're going to try figure out, well, what's this value here? And what's this value here? So we want to find where f of x is equal to 24. So I want to find where 32 minus 2 x minus 3 squared is equal to 24. So just like before, I'm going to use the idea of the square bracket, keeping it as is and working through it instead of multiplying it out. And we get minus 8. And I'm left with x minus 3 squared is equal to 4. So take the square root of both sides, you get plus or minus square root of 4. So you get two options. You say x is equal to 3 plus or minus 2. Option 1 with the plus. X is equal to 3 plus 2, so our x value is 5. Here x is equal to 3 minus 2, so my option is 1. So that looks about right. Here x equals 1, here x equals 5. So now that I've done that, we know that when we integrate our function, we're going to be integrating between 1 and 5. Again, I'm going to use my function as I found it in the last question because I can't work with that square bracket for integration. It has to be a basic polynomial. So when I integrate this, we get, as before, minus 2x cubed over 3 plus 12x squared all over 2 plus 14x, and that's between 1 and 5. When you work that out, you should get 352 all over 3. I'm leaving it in fractional form to make it as accurate as possible. And the area shaded is equal to this, 52 over 3 minus. Now, let's take a quick look. So this is the part which is not shaded. So the bottom bit here is 4 and the top bit is 24. So we're actually going to take away 4 by 24. So that is 96. So when I take away my 96 from my answer, we get 64 over 3 meters squared. So that is the new area that we had. So working here, we had the old area and we work with the accurate one. We have 72 meters squared. And we have the new area, which we worked out as 64 over 3 meters squared. So the percentage reduction is going to be old minus new over old. So that's 72 minus 64 over 3 all over 72. And to get it as a percentage, we're going to multiply by 100 over 1, which gives me 70.37%. So there was quite a lot going on in that last part of the question, basically having to work through what we had done over kind of 2 parts and then to put in the percentage reduction. So just to be careful, some errors that people made when doing this, not looking for the 1 and 5, instead using 0 and 6 for the x values. From the diagram you can see that actually the two values we want to integrate between are much closer together than the 0 and the 6. So make sure that you're keeping an eye on the diagram and does your values make sense. The next thing was that people assumed that the bit that wasn't shaded was the same as the bit that wasn't shaded in the previous question. And again, no, because we've changed that 1 and 5, we then change that bit that wasn't shaded as well. Just make sure you're okay with getting the reduction. Percentage change is always the difference over the original or old value, whichever way you want to look at it.